Welcome, everyone. My name is Professor Rood. I teach physical science, and my goal this semester is to get the lectures available for students to view online. I'm going to start with Chapter 1, which is entitled The Scientific Method. We're going to look at a basic overview of the basic physical science topics that we'll be covering. So let's start with the scientific method. When we deal with the scientific method, we must come up with a problem that needs to be solved. For instance, is Pluto a planet? From there, you make observations and perform many experiments. With the data, you need to interpret that data. And initially, a scientific interpretation may become a hypothesis, and upon further testing, the hypothesis may be elevated to a law or a theory. This process is ongoing, even though you may have a theory or law. As the scientific world changes and new information becomes available, theories can occasionally be overturned. Here's a flow chart, the scientific method. Let's state the problem. You experiment and observe, collect data, interpret the data, test the interpretation, collect more data from experiments, and this is an ongoing process. Let's talk a little bit about the laws of nature. Everything in the universe behaves in a certain regular way. We're going to call these the laws of nature. And in order to be a law of nature, there's a certain regularity that must hold true everywhere at all times. And we use these laws to predict things that are not yet discovered. So the laws of nature can give us an idea also of what is going on in places we cannot examine directly. For example, the sun's interior, or the interior of an atom, or the interior of the earth. So your textbook likes to say that laws tell us what, while as theories tell us why. I prefer to put it as theories are usually more than one idea and encompass several ideas, whereas a law is oftentimes just simply stated as a mathematical formula, such as Newton's law of gravity. So keep in mind, science is successful because laws and theories are not necessarily the final word. They are only valid as long as nothing else comes to light to indicate that they are no longer valid. I want to go over a few terms here with regard to the solar system. Polaris is the North Star, and its significance is that it happens to lie in the path of Earth's axis. And in the northern hemisphere, before compasses were available, people traveled by using the North Star because it appeared never to move in the sky. Constellations are the easily recognizable groups of stars like the Big and Little Dipper. And the planets that are visible at various times during the year to the naked eye are Mercury, Venus, Mars, Jupiter, and Saturn. Here's a figure of some common constellations, the Little Dipper, the Big Dipper, and notice that on the end here, the pointer stars of the Big Dipper points to Polaris, which is the last star on the handle of the Little Dipper. A little fast there, sorry. Let's talk about some early ideas of what the solar system looked like. And we're going to start with Ptolemy and the Ptolemaic system. Ptolemy was around between 100 and 170 AD, and he had a geocentric view. That is, the Earth was the center of the universe, and it stood in the center of the universe motionless, with everything around it moving in little circles or combinations of circles. Here's an image of Ptolemy's solar system. So we have the Earth here in the center, Moon, Venus, Mercury, the Sun out here. But notice the planets orbiting in these little circular patterns. The stars were close by on this inner surface of what they called the crystal sphere. Jumping ahead to the Copernican system, we're going to 1473, 1543, and he developed the idea that the Earth and all the planets that were known at that time rotated around the Sun, and they rotated in a circular path or orbit. He indicated that the Earth rotates daily on its axis, the Moon goes around the Earth, and the stars are far away. Copernicus is given credit for the correct system. He only had one thing wrong with his system. Pause the video for a moment and see if you can figure out what was wrong with the Copernican system. Well, it's the fact that the paths of the planets are not circular, but are in fact ellipses. Here's the Copernican solar system. About 100 years after Copernicus, Johannes Kepler, developed what are called Kepler's laws of planetary motion that explain how planets actually move. Now, Kepler worked with a very famous scientist, Tycho Brahe, and Tycho Brahe had a lot of data that he had taken himself of the positions of the stars. Tycho ended up dying, and all of that data fell into Kepler's hands. Since Kepler had worked for Tycho, he knew that the data was very good. So he started working with the data on Mars, and he worked 4 years on that. And he could not get the data from Tycho to fit any of the models of the solar system of that time. So he decided to discard the current theories on the solar system and look for a new cosmic design that fit Tycho's observations better. That's how confident he was in Tycho's data. So what developed from Kepler's work are Kepler's 3 laws of planetary motion. The first one corrects the orbit shape of the planets. They are ellipses, not circles. Now, they are not very elliptical, but if you are calculating where a planet is going to be in an orbit and you are using a circle versus an ellipse, you will not get the right information. And the Sun is sitting at one focus in the ellipse. And in an ellipse, there are 2 focuses. This is just showing a picture drawing an ellipse. Here's a focus, and here's the other focus. One of those focuses represents where the Sun would be. Kepler's second law is better demonstrated in a figure, but I'll state it here. A planet moves so that its radius vector sweeps out equal areas in equal times. Let's take a look at that. So here's an orbit. Here's the radius vector. So as the planet moves in orbit around the Sun, it sweeps out equal areas in equal time. So this means that area A is equal to area B, which is equal to area C. So what does that mean? What do the planets have to be doing? The planet have to be doing as it's orbiting the Sun? What happens to its speed? Pause the video and think about it for a moment. As the planet moves from A to B, C to D, E to F, where in the orbit is the planet moving the fastest? Well, the answer is E to F, because it's closest to the sun and gravity is helping it move along. The area C here shown in yellow, is this equal or equivalent to B and A, but what is happening is the planet is speeding up or slowing down depending on where in the orbit it is. The closer to the sun, the faster it is moving, and the greater the distance it is traveling here. A little bit slower there, and slowest furthest from the sun. Finally, Kepler's third law says the ratio between the square of the time needed by a planet to make a revolution around the sun and the cube of its average distance from the sun is the same for all planets. Let's look at this in formula. So the period of the planet squared, that's how much time it takes for a planet to orbit the sun, the Earth, 365 days, divided by the average orbit radius cubed, is the same for all planets. In other words, it's a constant. Can I fit that on here? All right. And it can be written in short form here. T squared, with T being the period of the planet, divided by R cubed is the same for all planets. Here's an example of proving Kepler's third law. And we have Saturn's satellites, Tethys, Dione, Rhea, and Iapetus. And if you calculate the period of the planet squared, and this is for Tethys here, 1.89 days squared divided by the average radius, 2.95 times 10 to the 5th kilometers cubed, you get this value right here. 1.4 times 10 to the negative 16 days squared per kilometer cubed. And that ratio is the same for all other satellites. So we can say that Kepler's third law, in fact, holds for this satellite systems. I think this is a good stopping point for our first video in Chapter 1, and we will continue on in Chapter 1 with Video 2.